welcome everybody. Today I wanted to talk to you about pH and also acid strength, but mainly pH. But before we get into pH, let's talk a little bit about acid strength. And so when we look at acids and bases as well, actually, there are some that are strong and there are some that are weak. And all this depends really on how much they dissociate or ionize. So for example, if I were to take one of the strong acids, and there are 7 of them, the 7 strong acids are HBr, HI, HCl, HNO3, H2SO4, HClO3, and HClO4. And I remember this, one of my students came up with this a while ago. Brickle, no, so, clo. Brickle, no, so, clo. Those are the 7 strong acids, HBr, HI, HCl, brickle, HNO3, no, H2SO4, so, HClO3, and HClO4, clo. So those are my 7 strong acids. When I look at any of these 7 strong acids, they all dissociate the same way, and that is completely. If I were to take HBr, for example, and I were to put it into some water, then what would happen is you would form H plus and Br minus. Now this happens completely. So if I were to have 1 molar of HBr and 0 of the products, the change would be 100%, minus 1 molar plus 1 molar. And so that would give me 1 molar of the products and 0 of the reactants. And this would be a complete ionization. If I were to look at a weak acid, which is not on the list, something maybe like HF, HF will also undergo the same ionization, but to a much lesser degree. It won't ionize nearly as much. So now if I were to have my 1 molar and 0, this might ionize maybe 2%. So that would be minus 0.02 molar, plus 0.02 molar, and plus 0.02 molar. So we'd have 0.02 molar, 0.02 molar, and 0.08 molar. Now look, the most important thing about an acid is the H+. This is what makes the acid what it is. We see in the strong acid that it's 1 molar, that's a lot more H+, compared to the same amount of weak acid. The 1 molar weak acid only produces 2% of that 0.02 molar. So this is to give you an idea. Strong acids, they ionize completely. They're strong electrolytes. They form more ions. We saw that in the lab. The light bulb lit up really well. When we tried a weak acid like acetic acid, the light bulb only lit up a little bit. There were less ions. The stronger the acid, the more dissociation there is. The more H+ there is, and what you'll see in this video is the lower the pH there is. Now for bases, there's also strong bases. Strong bases are all of the group 1 OH hydroxides and some of the group 2. And so those include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. And for group 2, starting with calcium hydroxide, strontium hydroxide, and barium hydroxide. And in fact, a good way to remember these, I don't have a Brickle, no, so, clo, but a good way to remember this is that on the periodic table, they form a lowercase b, the elements, and so it's group 1 and group 2. So these are our strong bases. Weak bases, they include all the other OHs that are not in that group, and also they include amines, including ammonia, NH3, and other amines that have carbon in them, like CH3 and H2. This N group over here makes it a weak base. Now, let's talk a little bit about pH. pH is a measure of how much H+ there is. It's based on water's interesting characteristic of something called autoionization. Autoionization is exactly how it sounds, automatically ionizing. So here's two waters, H2O and H2O. We saw this reaction when we did acid and base conjugates. One of the H2Os will act as an acid and donate, and one of the H2Os will act as a base and it will accept. Now when we see that happen, they become H3O plus and OH minus. They produce an acid component and a basic component. Now we can actually write a K value for this. The H2O are liquids, the H3O plus are aqueous, so my K for this, called Kw, will look like H3O plus times OH minus, which are the two products, over 1, because the H2Os are liquid, and this K value actually has a set value at a specific temperature of 25 degrees Celsius, which is 1 times 10 to the negative 14th. Now if I were to do a little ice table for this and have my H3O plus and my OH minus and do an ice table, I would start off with each one being 0, then change would be plus x, x and x, and so my Kw would be equal to x squared. And when I solve for x, 10 to the negative 14th equals x squared. If I take the square root, I get that x is equal to 10 to the negative 7. Each of them, the H3O plus, the acid component, and the basic component, are each 10 to the negative 7 molar. They're equal. We have equal amounts of acid component ions and basic component ions. Pure water is neutral. It has the same amount of acidic component and basic component. They cancel each other out. And this is because of the fact that it's just pure water. Both the H plus and the OH minus are coming from the same source. They're coming from the waters transferring protons or H plus ions between one another. Now this is pure water. This chapter is about acids and bases. And since we have our H3O plus here and our OH minus, if we add an acid to the water, adding an acid to a water will drive up the H3O plus. Since they both have to equal 10 to the negative 14th when they multiply together, driving up the H3O plus will in return cause the OH minus to decrease. When you add an acid to water, you're sort of shifting the equilibrium. It's basically Le Chatelier's principle. We're taking the reaction or the water and we're causing there to be a shift. So let's look at some examples in detail here and talk about what pH is. This scale right here, this H3O plus times the OH minus equals 10 negative 14th, when one increases, the other one decreases. This relates to pH because what I can do is I can make this a more convenient scale. I can do a log scale. If I take the negative log of the H3O plus, that is called the pH. pH stands for power of hydrogen. Hydrogen, or log, is a exponential scale. So we're doing the power of hydrogen. The negative log of the H3O plus is called the pH. The negative log of the OH minus is actually called the pOH. So if I go through with my formula right here, if I take the negative log of the H3O plus, I'll get pH. If I do the negative log of the OH minus, I'll get pOH. I'm multiplying them, so when I multiply logs, I add them. And if I take the negative log of 10 to the negative 14th, I will get 14. This is why the pH scale is governed by that number 14. And so what I end up having is these two equations that I circled sort of playing off one another. Now, if I look down here as their relation to each other, if I have something that has a pH of 0, it has an H plus that is 10 to the 0. If I have something that has a pH of 14, it has an H plus of 10 to the negative 14th. If I am somewhere in between, if I'm at pH 7, well then my H plus is 10 to the negative 7. And we could go in between any of these. If I had a pH that was 4, my H plus would be 10 to the negative 4. Now how does this relate to OH minus? Well, remember that they are inversely related, and they always multiply together to be 10 to the negative 14th. So if I look at my OH minus on the same scale here, when my pH is 0, my H plus is 10 to the 0, my OH minus is 10 to the negative 14th. This would be a case if you had something like hydrochloric acid. That would be very acidic. If, on the other hand, I were to have an H plus of 10 to the negative 14th, my OH minus is 10 to the 0. That would be a case where you had something really basic like sodium hydroxide. If you had 10 to the negative 7 OH minus, then you would have 10 to the negative 7 10 to the negative 7 H plus, you'd have 10 to the negative 7 OH minus, and you'd have something that was neutral like water. Then you could have different ranges. I gave you this example of 10 negative 4th. The OH minus would be 10 to the negative 10th because they multiply together to be 10 negative 14th, and that would be something that was slightly acidic like vinegar. You could have something like soap, maybe 10 to the negative 11 H plus with 10 to the negative 3 OH minus, and you'd have something like soap. Notice that even in the case where you have something that's highly basic, there's still a little bit of H plus there. And even in the case where you have something that's highly acidic, you have something where there's a little bit of OH minus there. You're never going to completely get rid of one of the ions because you'll always have some of them based on this equation up here. And they'll always multiply together to be 10 to the negative 14th. Although I don't list POH on this scale, we could do POH. The POH down here at pH 0 would be 14. At pH of 4 would be 10. At pH of 7 would be 7. And at pH of 14 would be 0. So you can see how they relate in that way as well. Now, how do I remember all this and put these together? Well, one way of doing this is, and here's the scale again, and this time we could talk about POH, but I've already done that. But here's how I put this all together. I put it all together in this diagram right here. Once you know one of the cornerstones here, H plus, OH minus, POH, pH, you can automatically figure out all of the other missing pieces of information. For example, H plus and OH minus, they relate to each other because H plus times OH minus equals 10 to the negative 14th. And now I could solve for OH minus or solve for H plus as I show you in the diagram. If I know H plus, I can take the negative log of it and I could find the pH. If I know the pH, I can do 10 to the negative pH, the antilog, and I could find H plus. If I know the OH minus, I can find the pH by taking the negative log of it. If I know the POH, I can find the OH minus by doing 10 to the negative POH. And if I want to relate pH to POH, I know that together pH plus POH equals 14, and so now I can, as I show you here, I can rearrange them and solve for either one. So this is my pH square here. It allows me, once I know one of these substances or one of these values, to automatically solve for any of them. And so, here's some practice for you. Let's see if you could try this one right here. These are strong acids, so they completely dissociate, and all we need to do is plug in the values. I'm giving you 2 molar HNO3, So that would be 2.0 molar HNO3. So that would produce H plus and NO3 minus. That would produce 2 molar of these. So now I know my H plus. My H plus is 2 molar. Notice I have it as H3O plus in the problem. They're interchangeable, and we could talk about why in class. It's a good thing to discuss. Now, if I wanted to find the pH, I would do the negative log of H plus. Negative log of H plus, the negative log of 2. Let's see what we get there. So if we do the negative log of 2 log, we get negative 0.301. Notice it's a negative number because it's such a strong acid. pH generally goes between 0 and 14, but here it's a little bit lower. Now I can do OH, so this is pH. POH, I just subtract 14 from that. And I get 14.301. And now if I want to do the antilog of that, I would get, I would do 14.3, so I would do that negative. So I would get something really, really small, which would be 5.01 times 10 to the negative 15. Now what I'd like you to do is like you to try that for these values too, to look at the pH, the POH. And I'd also like you to try this for OH minus, for NaOH here, and finding OH minus when I give you the pH. We'll go over these tomorrow in class. All right, thanks so much for watching.